Okay,
So
great.
you are good to go.
All right. Yeah. Thank you, Professor, for the introduction. Um, so in the first two talks in the series of machine learning, we have covered the basics of supervised learning. We have introduced deep neural networks. And in the second session by Ashwin, I think we went into a bit more detail on deep learning. We covered different deep neural network architectures like convolutional neural networks and recurrent neural networks for different types of inputs. This session is going to be an introduction to a new and exciting area of machine learning that is, in some sense, closely related to deep learning. It's called adversarial machine learning. This is going to be an introductory session of this field. The outline for the current talk is as follows. First, I would give some motivation and overview of what adversarial machine learning is. Then we will delve into a bit more detail on what are called adversarial attacks. We will discuss different kinds of attacks that machine learning algorithms can be subjected to. And then we will discuss defenses against these possible attacks.
Monique,
And towards the end of the presentation,
I'm sorry for interruption.
yes.
There is
Mhm.
some disturbance in sound. Is it you are also able to hear, or it's from your side?
Um,
Some,
from my side, I don't see any disturbance.
okay.
Is the disturbance still there?
Anyone else can hear disturbance, or is it only I am hearing?
Yes, sir. The voice is little bit noisy.
Little. I don't
Hmm,
know. Maybe I don't know. Maybe I don't know why it is. Huh? Mm, mm, yes.
I see.
Uh,
Is it uh, breaking up in the middle, or
and yes, and little bit.
is it just
I don't know how to put it, but it's like some cracking or
hmm,
somewhere. Okay. Mm, mm,
okay?
mm,
That is weird. In the first talk, we didn't have that, right?
mm. Yeah, okay, I think it's okay. You can go. Okay.
Okay.
Mm.
Let me know if you would like to repeat anything, if I
No,
haven't
it's a clear.
said
Only there is
properly,
a.
or if you want me
We are able to hear. Only things the quality is no. Okay. That's all right.
to. Okay.
Mm.
All right. Right. So on with the outline. Once we cover the adversarial attacks on machine learning algorithms, we will discuss defenses against adversarial attacks. And towards the end of the presentation, if we get time, we will cover a game theoretic view on adversarial robustness, which I think is also very interesting. Feel free to stop me anytime during the presentation also if you have any questions. All right. So now with motivation and overview. So I would like to start by introducing this unreasonable success of deep learning, right? You must all be aware there is a lot of hype around deep learning, especially in the recent years. Deep learning has managed to solve or achieve state of the art in several different types of machine learning tasks, various tasks in computer vision, reinforcement learning, game playing, audio processing, etc., etc. And very recently, it was in the news that a deep learning algorithm from this company DeepMind has managed to make progress on protein folding problem that remained open for like 50 years. And some of these pioneers of deep learning now they're saying deep learning is going to be able to do everything. Or, for example, Andrew says AI is the new electricity. Um, so amidst all this hype, I think a very good case study for deep learning success is this ImageNet competition. So this competition is about image classification. ImageNet is a very large data set that composes of around like I think more than 10 million images. So the competition is about training on this very big data set and building an algorithm that tries to classify these images into one of these 1,000 categories. Um, So this happens once every year. It started in 2010 and it went on in this format till I think about 2017. And in the year 2012, there was this entry of this algorithm called AlexNet by one of the students of Geoffrey Hinton. And this was based on a deep convolutional neural network architecture. And it beat the state of the art and also all the previous algorithms in performance by 10 percentage points. And that was a big jump in the state of the art. And from that year onwards, year after year, people have been building bigger and better deep learning based architectures for this problem of image classification. And by the year 2015, we have actually managed to beat the human level accuracy in this task. So machines are able to better classify these 1,000 categories of images even than humans. And the graph here at the bottom indicates the error percentage of the top performing entry into this competition for every year. And by 2015, we got error below 5%. So what are the implications of this? Does this mean that this problem is completely solved? Does this mean machines are actually better at image understanding than humans now, at least over this narrow task of image classification? Of course not. And very quickly, people began to discover these tiny problems with these state-of-the-art deep learning algorithms, especially these things called adversarial examples, which have been found around year 2014. So what adversarial examples are basically tiny perturbations that you do on top of the input data, and that perturbation is designed carefully so that upon adding that perturbation, the input gets misclassified even by the state-of-the-art algorithms. So that's what adversarial examples are. Here, in this specific example, the input X to the algorithm is an image of a panda. And the algorithm initially classifies this image correctly as a panda with 57.7% confidence. But now there is an adversarial agent, a malicious entity, who crafts this noise looking perturbation and scales it by very small number and adds it to the image. So after this corruption, the final image looks almost identical to the initial image to the human eye. But then to a machine, this apparently looks very different. And even state of the art machine deep learning based algorithms make a mistake in classifying the perturbed input. And not only that, they classify it wrongly with very high confidence. Here, the network is classifying this image as a gibbon, which is, I think, some sort of a monkey. And that happens with 99% confidence. So this phenomenon of adversarial examples since then has been uh, found to be the case with almost all deep neural network based architectures, and it doesn't even depend on specific kinds of data or specific kinds of data points. It's like all pervasive. It's a real problem.
Muni, I have a question.
Right.
So when you say add the
Yeah,
noise,
sure.
so this add the noise, so
Hmm.
I think you are telling that it's a carefully designed noise, right? It's not a random noise, right?
Yeah, correct. It's not random noise. It's just designed by some other optimization algorithm that is specific to this input image and this particular algorithm. It's
So
not something like Gaussian random.
does this like when say you when you say this is a optimized noise, that means it has also some specific kernel, right, to mislead the algorithm.
Yeah, correct. It is like specifically designed for misleading the algorithm.
Okay, okay, thanks.
Yeah, right. So these attacks on input images, these are termed as adversarial attacks. So basically, the goal here is to change the input data point slightly so that the label changes. So the task is modify a data point x to some other close data point x plus delta, such that the prediction on x, f of x, is different from prediction on x plus delta. And here there is a constraint. The constraint is that the perturbation should be slight. So of course we can make x and x plus delta be different in this output if delta is very large, right? So the challenge here is to design attacks such that delta is very small so that humans will not be able to tell a difference, but the network or the deep learning algorithm will be able to tell the difference. So this slight change usually is measured in some norm constraint. Uh, so that is to say that the norm perturbation of this added noise is bounded above by some very small number like epsilon. So here I have given many examples for these adversarially generated images. So on the image on the right, you have this MNIST dataset, handwritten digits. And for every image, you have these three images. Those are all adversarially corrupted versions of the original image. And each of these images in the adversarial column are wrongly classified by the network. And for each row, the perturbation is done in a different norm. For example, in the first row here, the perturbation is done in L1 norm. That means the change in pixel values, when you add them up together in all of the image, the whole sum should be less than or equal to epsilon. And for the final column here, it's in a different norm, L infinity norm. What that means is the maximum pixel change across all the pixels in the image is bounded above by epsilon. And no matter what kind of norm you use, it turns out that adversarial examples can be easily constructed. And it's not even specific to some specific classes of data, not specific to any data sets also. So on the right hand side, you have color images of higher resolution than MNIST. And you can distort these input images by some noise and make them classify into any class that you want. For example, here there is an image of a temple, and you distort it with some specific kind of noise and make the network think that it's an ostrich. And in fact, you can target a specific class to fool the network. So for example, suppose you have an image of a dog and you want the network to be classified as some particular class, say ostrich. You can craft your noise exactly so that the network will be fooled into thinking that this particular image is ostrich. So these are the adversarial attacks. Now, these adversarial attacks, they come in all kinds of interesting forms. So, for example, this imperceptible to humans, that constraint can be interpreted in a lot of creative ways, right? So, in the previous example, this imperceptibility meant that each pixel value is not changing by much, but almost all the pixels in the image are changing to some extent or not. One can modify that constraint a bit and say, what if you only want to change a few pixels in the image and still fool the network? And it turns out that even that is possible. Uh, there is an attack called adversarial sticker attack. So what the goal of that attack is to construct these small, weird-looking images and print them on stickers in the real world. And if you put them next to the object and then give that image to the neural network, then the neural network classifies it wrongly. So here in the above image, you have the image of a banana, and the network classifies it correctly as a banana. But then in the below image, you just put this adversarial sticker next to the image of the banana, and now suddenly it gets classified as a toaster in this case. And there are other kinds of interesting adversarial examples. So on the right hand side, uh, there is an adversarial attack on a face recognition uh, uh, deep learning algorithm. So on the top is a researcher who is an author of the paper that proposes this attack. He's wearing these funky looking glasses with some specific pattern of some colors printed on it. And that pattern is the adversarial attack here. And to a human, a person with the glasses or without the glasses on would look approximately like the same person. But with the glasses on, the deep learning algorithm now is pulled into thinking that this person is very similar to this female celebrity here. And similar attacks have happened in different forms across different neural network architectures, across different tasks.
Moni, it's very interesting. We have
Uh,
a science fiction and movie. Uh, uh, so just
yeah.
uh, just jokes apart, but see, you have a multi-object this detection also, right? Huh? So the
Hmm.
question is that when you put this sticker or page, so want because although maybe it's like regional this CNN or something, so this sticker is not classified separately or just it's uh, destroyed the whole image itself. See,
So the sticker can be designed with different purposes.
uh,
So like you can make the sticker so that the object detection algorithm does not detect anything. So suppose you train it to detect people on the road or something. So it's supposed to draw boxes around humans when it sees the humans. And suppose you put this sticker on top of the shirt of that person. Now you can make the algorithm into not detecting that person at all.
and
So
it
that kinds of attacks are also there.
and it would be regional, right? It's not required to be on the whole image, right? Just on the page of
Yeah,
that.
it's not required to be on the.
Yeah.
Yeah.
Hmm. Okay. 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 Thanks.
And these attacks are like sometimes even more extreme than what I have shown here. So in this particular research work, the authors managed to construct adversarial attacks by just perturbing one single pixel in the whole image. So here, for this image, which is of a shape, the network correctly classifies it as a shape. But you change this one single pixel value here. And with that one change, now the ship becomes a car to the network with very high confidence. And that happens with different kinds of images. And again, as a reminder, this one pixel that is modified, it's not randomly chosen. It's chosen by some algorithm so as to specifically fool this particular network. But the overall lesson is that uh, the constraint placed on the adversary is imperceptibility to humans, and that can come in many forms. And these adversarial attacks are not just limited to images. Um, Researchers have even come up with adversarial attacks for audio data. So here there is a deep neural network whose task is to transcribe voice, right? Given some audio clip, it will print out the words that are said in the audio clip. And now to the audio clip, one can add this carefully crafted adversarial noise. And the human ear cannot even hear it because it's very low amplitude. But to a machine, the transcription now is completely jumbled because of this adversarially added noise. And adversarial attacks also exist for other forms of machine learning tasks. Like there are even adversarial attacks for reinforcement learning. But in this talk, I'm focusing on supervised learning because that's the simple setup. Right. So, of course, these adversarial attacks, if they are just limited to these toy examples in on like only on the computers, then that won't be of a real world effect, right? But that's not the case. Now, machine learning algorithms have been used in safety critical applications, like in self-driving cars, right? And that would actually have serious security implications because of these adversarial attacks. So imagine a self-driving car. The algorithm is pulled into thinking that a stop sign is actually a speed sign. just by placing some sticker on the speed sign, and that that is a serious security implication. And this has actually happened in real world. So this article is from April 2019. This a Chinese company called Tencent, they have managed to print out these adversarial stickers, and if you place them on the road somewhere, a Tesla autopilot algorithm would swerve into the wrong lane because of these placed stickers. So it's a real world thing, and the risk is real. And another example that I want to share regarding the security implications of adversarial attacks is the medical diagnosis example. So in recent times, medical diagnosis, uh, people have been using deep learning based algorithms like convolutional neural networks to diagnose diseases based on X-rays or other medical scans like that. Essentially, you treat the scan as an image, and now an adversary can try to come up with an attack to change the image very slightly, but fool the algorithm into diagnosing a particular patient in the completely wrong way. So you can make a healthy person uh, into thinking that they have the disease, or you can hide the disease. So any targeted attack is possible. Right. So that's sort of overview of what's happening with respect to adversarial attacks. Now that we have some background, I would like to formally introduce what adversarial machine learning is. It's the study of machine learning in the presence of these malicious entities called adversaries. It's a relatively new area. I would say the area composes of two uh, primary parts. Like one part of the adversarial machine learning is to do with algorithms. And here the task is twofold. On one hand, you want to design effective and efficient new adversarial attacks on different kinds of machine learning algorithms to test their robustness. And on the other hand, you also want to develop defense mechanisms, defense methods to counter against these attacks. And besides the algorithmic part, there is also theory, because the cause and the origin of adversarial examples is still not completely understood. So analysis of why adversarial examples occur in different scenarios and to what extent they can occur, and how much they can decrease accuracy, um, for instance. So understanding these fundamental limits is part of the theory of adversarial machine learning, and that's personally my area. There are a lot of open questions in this area. Um, it's an exciting field to be in right now. All right, so that's an overview of adversarial machine learning. Next, we will discuss these adversarial attacks in a bit more detail. We will go through how these attacks can be constructed, actually. So before I start with this phase, if you have any questions or like any clarifying remarks, uh, you can ask now.
Oh, I will ask because it's very interesting. So, do you also need a
Sure.
same set of data set to create this, like training?
Yeah. Um so the attacks that I have shown
Hmm.
right now, they all occur at the test time. So the algorithms have already been trained on some data.
Hmm.
And to perform these attacks, the attacker need not even know the training data at all.
Hmm.
So they can just craft these perturbations using the weights of the trained algorithm.
Okay.
But there are also some other kinds of attacks that need training data to work. Um, it's a
So,
mix of both.
so there are like two questions since you from your explanation. One is craft. Okay. So craft is
Mhm.
like craft you design by like some features, or otherwise you learn that craft also, right? So
Right.
when I have to this learn the craft, I will put up some things and see that whether it what how do I want to pull it, right?
Mhm. Yeah.
And then based on that, I will put up my weights. So, so fooling will become supervised. I know that what is the target things, and I may limit it to few pixels, and then this will be a like targeted fooling, kind of.
Right. Yeah.
So
Yeah,
I
that's a
don't.
good point. Actually, there are two kinds of attacks, like targeted or untargeted. So,
Uh,
like adversary might think it wants to specifically target
uh,
like some class, like maybe it wants some dog to look like an ostrich to the algorithm.
uh, uh,
So in that case, the objective is clear. Like you want to make the algorithm think that it's this particular class. So you can train based on that. There is also an untargeted attack. Basically, there the objective is to just make the algorithm misclassify. It doesn't matter what it classifies it as. So you can make the dog into any other thousand classes that are there, but you just make the network into thinking that it's not a dog.
so just
In either case, like
sorry.
Mhm.
So my question was that
Yeah,
how do you
that's fine.
change the weight, because some policy should be there for perturbing the weight, right?
Right, that's another good point. So there I want to clarify the adversarial attack, the adversary who is performing the attack, he need not change the weights of the algorithm. He's only changing the input, right?
Okay.
He's only adding that noise to the input. So the algorithm still remains untouched.
Okay.
So
Okay. I am
that
sorry.
part is out of the hands of the,
Hmm.
yeah,
So there is a question one, maybe we can take later on, but it's, does this
right.
disturbance depend on the particular algorithm or network? I think yes, right?
Yeah,
Hmm.
yeah. So this disturbance is crafted specifically for some specific algorithm, for some specific set of weights, in fact. We will actually see how these attacks are crafted. I think that will give better clarity.
Okay, so you carry on.
All right. Yeah. So primarily there are two kinds of attacks that are studied in literature. There are more kinds of fancier attacks which are like a mix of these both, but for now we will stick to explaining these two attacks. So recalling from the first talk, we have these two different phases in the machine learning pipeline, right? There is this training phase where the algorithm is trained on some data, and the goal is to learn some function that maps inputs to labels. And in the testing phase, given some new data point X, the goal is to just output a prediction Y hat. So depending on what phase the attacker is attacking, we have different kinds of attacks. So in evasion attacks, the corruption is done in the testing phase. And the goal is to add this small noise to the testing data point so that the prediction y hat for x plus delta here will be different. So the attacks that we have seen previously, the single pixel attacks and all of those are actually evasion attacks because they don't need to know anything about what happened in the training phase. They only occur at test. The second kind of attack is what's called a poisoning attack. And here the corruption is done in the training period itself. So the corruption is done in this sense. It's basically modifying some small fraction of the training data points to whatever the adversary wants it to be. And the goal here is to corrupt the performance of the algorithm. So with slightly different training data, the algorithm learns slightly different hypotheses. Right? Now the goal with a poisoning attack is to make the algorithm learn a very bad hypothesis that will have very low true accuracy. So those are the two kinds of attacks. Now we will see how each attack can be constructed. Like first we will see about evasion attacks. And for this, let's try to recall the supervised learning setup. In supervised learning, the goal is to learn some optimum set of weights, W hat, and the weights should be such that they minimize this loss function over all the training data points. And the method to do that is through gradient descent, usually, or stochastic gradient descent. In each iteration, you update the weight vector by taking the gradient of the loss with respect to the weight W. So in neural network based algorithms, this gradient descent is done with back propagation efficiently. Now it turns out that constructing this untargeted evasion attacks, the goal is very similar to the goal of a supervised learning algorithm. So instead of minimizing the loss, the goal now is to maximize the loss. The second difference is instead of playing with the parameters, the goal is to play with the input x. So the goal of an evasion attack is to construct this delta hat, which maximizes the loss such that this delta is added to the input and delta is also bounded by this norm constraint. And this constraint here basically is to ensure that the image doesn't look very different to a human. And just like in the case of supervised learning, we can still use gradient descent to solve this optimization problem. So we initialize this disturbance delta say to 0, and in every iteration we calculate the gradient of the loss with respect to input x, and we take a gradient ascent step. So if you compare this equation here to this equation here, firstly, in the normal gradient descent for learning, we take the gradient with respect to the input w, with respect to the parameter w, sorry. Here we take the gradient with respect to the input x. And here we actually do a descent because the goal is minimization. And here we do an ascent. That's why we have a plus sign because the goal is to maximize the loss. And we also have this extra projection step because after taking the gradient step, in case this constraint is violated, you just adjust the delta so that it's within the constraint region. So that's why there is this small modification of using a projected gradient descent. But the basic mechanism is still simple. It's just performing gradient descent on the loss, but with the goal of maximizing. And the gradient descent now is performed with respect to the input x. And this attack is called the PGD attack. And actually, many of the adversarial attacks that I presented at the start of the talk, they are constructed using this very simple method. So here in this medical diagnosis paper, you can see this PGD is the method that's used to generate these adversarial examples. So all you need to do is perform this projected gradient descent. You need to decide on some appropriate step size and pick some number of iterations, and you will get a very good attack. And again, so that attack is specific to this particular loss and this particular F, right? So of course it depends on the particular algorithm that we are using. It's not noise at all. It's just the output of this optimization algorithm. So that's how evasion attacks are constructed. Now let's move on to poisoning attacks. So here the goal is to corrupt data in the training phase. Right?
Moni, I have a question, one question here. Okay.
Yeah,
So,
sure.
but for training, still we needed that network weight we need to know, right? Although we are not changing the weight
Um,
for computing the loss,
yeah,
the network are
yeah,
required.
that's a good point. Yeah. So the adversary needs to know what weights are there in the algorithm. It won't change it, but it needs to know them
Okay.
for computation purpose. Yeah.
So kind of it need to know what is the policy is applied for training.
Yeah, exactly. Yeah. All right. So next we move on to poisoning attacks. So here is a simple example of a binary classification task. Suppose we want to learn like a linear separator between these two classes. The goal in poisoning attack is to corrupt certain fraction of the training data so that the true accuracy of the algorithm is damaged. So for example, here, the adversary has picked this point here and moved it somewhere here. And because of this one change in the data point, now the algorithm learns a completely different decision boundary. And that can have very bad accuracy in general, right? Suppose the distributions are spherical like this, maybe like Gaussians with centered means there. And now with the true distributions, the loss for this new decision boundary will be very bad compared to the original decision boundary. And the way to construct a poisoning attack is you need to carefully choose which training data points to change, right? Because your budget is that you can only change some small fraction of the training data points. So what you do is you identify something called the influence of each data point on the decision boundary. So for example, if your algorithm is like a max margin learner, something like a support vector machine, there the goal is to learn a decision boundary such that this margin is maximized. And it turns out that in an algorithm like this, the data points that are close to the boundary have a lot of influence on the decision boundary. So if you change a data point that is close to a boundary even by a little bit, the decision boundary can change by a lot. So you compute this number called influence of each training data point on the decision boundary, and you basically maximize the influence of the corrupted data points. And using this optimization, the adversary can craft a successful poisoning attack. Right. So that's about poisoning attacks. Um, Examples for evasion attacks are all the attacks that I have shown at the start of the talk. So here for a poisoning attack, I include one additional example. So in this paper, what the authors do is add one small perturbation to exactly one training example. So in the whole training data set, they're only changing one single image, and that single image also they're only changing by a little amount. And because of that one change, the weights that are learned by the deep learning algorithm are slightly different. And that slight difference was enough to make it wrongly predict the classes for multiple test images. So the accuracy dropped by a noticeable amount. That is a surprising result. Right? So this is an example of a poisoning attack because you are interfering at the training time. All right. So that's the explanation for how the attacks are constructed. Now we will move on to defense methods for these attacks. So before we discuss a successful defense, we have to, I think, understand fake defenses to some extent. It's because in the recent years, especially, there have been a lot of defenses against these adversarial attacks that are proposed. And once the paper is published, before even the conference happens, the attacks have been broken by some other paper. Uh, Sorry, the defense has been broken by some other paper with a new attack. So at least in the current stage, it seems like attacks are a lot more powerful than defenses. So we need to be very careful in declaring that a defense is successful. So for that reason, I'm going through some failed defenses, and then we will see one successful defense. So again, to recall, evasion attacks are constructed by maximizing the loss function. The maximization is done with respect to the input parameters, not with respect to W. So usually one should expect the adversary to solve this maximization with some kind of gradient algorithm. So they will need to compute gradient of the loss with respect to the input. So a lot of defenses are motivated in this way. They want to block access of gradients of the loss to the attacker in some way or the other. So the first strategy of defenses that don't work are as follows. So the first strategy of defense is include this non-differentiable transformation of x. So what this means is instead of directly computing the prediction on the input image x, you first transform the input image in some non-differentiable way. Say you apply JPEG compression to it, or maybe drop some random pixels here and there, and then try to fill in the gaps with something else. So you do some transformation that is not differentiable, and then you apply the inference on it. You then apply f on top of this new transformation. And so suppose here the g is such a non-differentiable transformation. We would still want g of x to be close to x, because if the transformation is completely ruining the image, of course the network will predict it wrongly. So you want the transformation to be non-differentiable, but also kind of still maintain the integrity of the image. So g of x should be approximately equal to x. And instead of evaluating f of x directly to give out the prediction, you evaluate f of g of x. And the reasoning for that is, if you do this procedure, the loss can be computed only if f and g both were differentiable, right? Otherwise, you cannot apply the chain rule and do the backdoor. So one could think maybe this defense would be successful. But it turns out that it's not. All defenses that are based on this kind of transformations, they can be broken quite easily. And that's through an application of chain rule. So you take the derivative of f of g of x, right? So that's derivative of f times the derivative of g of the inner value. So here what happens is, using this constraint that g of x is approximately equal to x, the gradient of g of x, even though it doesn't exist because g is not differentiable, we can just replace it with 1, or the identity matrix in the case of vectors. And that gives this approximate value of gradient. And it turns out that this approximate gradient is enough to still perform this projected gradient descent algorithm that I showed before. And you can still come up with successful attacks. So that defense doesn't work. Another defense that doesn't work is making the inference process noisy. So here, the defender wants to wants to introduce some kind of noise in the process so as to fool the attacker. So instead of evaluating f of x directly, you will evaluate f of t of x, where t of x is some randomly generated function. An example for this would be, before computing the output, maybe you randomly drop some pixels in the image, or maybe add some noise. The hope is that these random transformations will somehow drown out the carefully crafted distortion of the adversary, and maybe the output would not be influenced by the distortion anymore because there's already some added noise to the process. So, but it turns out that these class of defenses also don't work, because the adversary now can just try to attack with multiple instantiations. So they can just run the attack, the gradient step, different times, and in each time the noise is slightly different. So if you average out that noise, you still get a good value for the gradient, and that approximate value is again enough to maximize this loss. Now, one could think of a simple defense, like what if we just completely block access to the model, right? Like the adversary, it needs to know what this f is and what the weight vector is to compute the gradients. What if you just don't give the adversary that access? So an example for that would be like these deep learning APIs that are published by different companies, right? So in these APIs, the access to the algorithm is only given through this interface. So you can upload an image or a test data point. The algorithm runs in some cloud, and the output is given to you. But the attacker now has no idea about what algorithm is running in the cloud and what the network architecture is, what the weights are. So this is called a black box model. So from the attacker's perspective, the whole algorithm is now just a black box. You can only pass in inputs and see the output. And it turns out that this is sufficient. You don't actually need to know the algorithm in detail. So what is done to break this sort of defense is to just compute gradients indirectly. So there are various ways to do this. Like one of the ways is to uh, probe this black box repeatedly with slightly different inputs and indirectly calculate gradients. And the indirectly calculated gradients are sufficient to maximize loss. One could also train like a surrogate model that is similar to the model that is in the cloud. And then once you train your model, the surrogate model, and craft an attack to this model, the same attack can be transferred to the model in the cloud. So here there is this phenomenon that if you craft adversarial examples for one deep neural network architecture, the same kind of adversarial example seems to work with similar neural network architectures. So that's the fact that is being used for this attack. And this is also widely happening in practice. Like for example, I've started off with this news article on how this Chinese company attacked Tesla's self-driving algorithm, right? So this company does not have access to what deep learning algorithm Tesla is using in their cars, but they still managed to attack that algorithm because they had this black box access. They could make the car see different kinds of scenarios and see how it reacts. So by doing this repeatedly enough number of times and by training their own models, they were able to still uh, break the defense. So it's not even enough to just hide your model parameters. Attacks are still possible. Right. Now we move on to one possible successful defense that actually seems to work in practice. Um, Again, we recall the supervised learning setup. Goal is to minimize the loss with respect to the weight parameter W, and it is done through gradient descent steps in the weight space. In adversarially robust learning, we change this into this min-max objective, right? So instead of minimizing the loss, you minimize the worst case loss. And the worst case loss is computed with respect to all possible transformations of the input. Now we just need an algorithm to solve for this min-max loss instead of just like this minimization problem. And that motivates this defense called adversarial training. Um, so the goal here is to uh, uh, train for this min-max objective. So here there are two loops in the algorithm. In the inner loop, we try to solve this maximization problem using PGD. And in the outer loop, we try to solve this minimization problem using gradient descent like this. So it's like this. So in every iteration, you do the optimization yourself. You craft the attack yourself and try to come up with the best adversarial example. Now you take a gradient descent with respect to that best adversarial example. So you make your own enemy and you learn to beat the enemy. And if you do this repeatedly enough, you get a successful defense. That's the logic behind adversarial training. All right, so we are nearing the end of the presentation.
It's
Maybe
all right, Muni. It's
we
all right.
can.
Very interesting. You can continue.
Okay,
And it
right.
looks
So I
like
just have a couple more slides.
that's all. And that looks
Yeah,
like that actor critic type things, right?
yeah, that's an interesting analogy. Yeah, yeah, it's like a game between the adversary and the algorithm.
So you train the
Yeah,
network like when even you have a worst attack, your network is optimized to predict right.
yeah, exactly. Yeah. So, but this thing is done greedily, right? So for the current input image, you build up the attack and
Uh,
then you take the gradient step in that direction.
uh,
But like we don't know if just doing this process will guarantee protection against adversarial attacks on all possible X, right?
mm,
That is, I think that's still an open question. But at least in practice, it seems like if you just do these iterations enough times, you will actually get robustness to even new unseen inputs.
Just to add to that, I think this is pretty common in H infinity control. I don't know if you're aware of it. I don't know if you've heard of it, but Professor Kothari and
Mhm.
maybe some other people would already know that this is exactly the kind of formulation you would have in what is called H-infinity control. Uh, if you're trying to
Hmm.
find the optimal control for some cost while you're minimizing, with the given control inputs, you would also include this sort of max over your disturbances, the worst disturbance that you can expect in your system, while you tend
I see.
to minimize the cost. So which means that gives you robustness. And this has been there for quite some time, 1970s, 1980s. If you are really interested, maybe you can actually check H-infinity control. It's again, uh, the idea of
Yeah, I
H-infinity
should
is it's
check
a
it
norm
out.
space. The disturbances are worst in that norm space, which is kind of very similar to what you're looking at right
Hmm.
now. I don't know what sort of norm you are taking here, but you can take different norms and that will give you different sort of behaviors.
So yes, Ramna is right. So what you
Right.
instead of the minimizing the disturbance, you minimize the maximum norm of the disturbance. Okay.
Yeah, that's exactly the idea here also.
So
Hmm.
then you guarantee
Yeah,
that
that seems very interesting.
that's guaranteed that against that norm.
Hmm.
Hmm, hmm,
Right.
hmm, hmm, hmm,
Yeah, I should explore this H infinity control. Maybe there is some deeper connection.
hmm,
And I'm pretty sure some of the things that this machine learning community have been discovering, some of them are rediscovering things that have already been
hmm.
done in other areas.
So
It just happens with new names.
I feel somehow it has been taken from the control people.
Yeah, that might be true.
Because
Yeah.
even neural network was used for like for control things earlier. Uh, so it was
Oh, I did not know that.
heavily it was
I
used
see.
neural network for adaptive control.
Uh-huh.
Am I right? Around 1970s again by that Narendra and other things, right? Or
Yeah,
I.
true. Yes, they try to include some neural networks for adaptive control. Yeah.
Okay.
Yeah, maybe a lot of things are already discovered in aerospace departments, and then these computer science departments copy that stuff. All right, jokes aside, in the final two slides, I would want to give this game theoretic spin, right, on what's happening. Essentially, what we want to do is try to look at this adversarially robust learning objective as a min-max game. So for the single sample version, you have this objective. Uh, the inner maximization is done by the adversary, and the goal is to choose some x prime, which is in some small ball of radius epsilon around x, so that the perturbation is imperceptible. And the goal of the algorithm is again to choose some w, weight vector. So one can think of a population version of this. So in the population version, the goal of the adversary is to choose some distribution mu prime that is different from the true distribution, but still kind of close to the true distribution. So in the distribution space, the adversary tries to change the distribution from the true one so that the risk here is maximized. And of course, the algorithm tries to minimize. So here, risk is the expected loss across the whole sample space where the samples are drawn from the true distribution. So you can think of this as a game of two players. Player one is the adversary. It chooses the distribution so as to maximize the loss. And the algorithm chooses the weight so as to minimize the loss. So it's a zero-sum game. And the action space here is continuous. It's also not the same. So player one's action space is the space of distributions, probability distributions. And action space for player two is the hypothesis space, the set of algorithms that the learning algorithm, the set of parameters that the learning algorithm can learn. And the basic question you can ask is like, does there exist a saddle point, right? Is there a min-max equality? Is there a Nash equilibrium? I think in the general case, it's still an open question. But one of the results that we recently got, uh, like working with my advisor, is this min-max inequality for one specific version of this game. So we consider this binary classification setup with 0, 1 loss. Input space is some Euclidean space, d-dimensional Euclidean space. Suppose you have P0, P1, the true distributions of data points coming from class 0, class 1. There are only two classes here for simplicity. And the hypothesis set here is the set of all subsets of the space. So for any set A, now the algorithm that has the parameter A classifies all points in A as class 1 and all points in A complement as class 0. And suppose we use 0, 1 loss function. 0, 1 loss function essentially means loss is 1 if you predict incorrectly and loss is 0 if you predict correctly. In this case, the true risk can be written in this formulation. Like suppose with half probability, you see a data point that's from the original class 0, but if the data point belongs to the set A, you would classify it incorrectly. So this part of the error is split from 0 to 1. And similarly, this part of the error is when you make an error by incorrectly classifying a class 1 data point as class 0. And it turns out that for this specific scenario, we have this duality theorem, which says that you can switch the min and max, and the final objective remains the same. There is a saddle point, and in fact, the saddle point is characterized by some optimal transport notion of distance between the data distributions. All right, so that's the end of the talk. For a brief summary, we have seen various kinds of adversarial attacks on machine learning. In more detail, we have discussed two types of attacks, evasion attacks and poisoning attacks. We in fact actually saw algorithms for constructing these adversarial attacks. And then we saw some failed defenses, and then one successful defense, that's the adversarial training. And finally, towards the end, we saw like some of my own work, which is on the fundamental limits of adversarial robustness and how it relates to this game theory. Okay, that's all from me. If you have any questions,
So
you
thanks.
can ask.
So we just stop recording and we can have a discussion because otherwise video will go long.
Sure.